Hello everyone, in this video I'm going to show you how to do geometry calibration using the city reconstruction plugin in Dragonfly. So by say geometry calibration, we typically means first the rotation center finder and second one the tilt angle finder. In current city reconstruction plugin, we have 6 different algorithms for the rotation center finder and 1 algorithm for the tilt angle finder. I'm going to show them one by one. So first, let's use a parallel beam dataset as an example. So I use the same dataset as I used in my last parallel beam reconstruction tutorial video, which is a fiber reinforced ceramic composites dataset. Again, thanks Aly from University of Colorado for sharing this dataset with us. It was acquired from a synchrotron micro-city beamline. Okay, so to use the rotation center finder or the tilt angle finder, you need to first select the projection dataset, which is ceramic composites, and select the beam type as parallel beam, and have all the other parameters available except the rotation center offset. So we have our minimum angle, angle step, and detector spacing ready to use. Also select the reconstruction engine. In our case, we use RTK FTK as a mask ratio 0.9. Now we can click on the Find Rotation Center push button. Okay, now we see 5 different algorithms. So among those 5 different algorithms, the first 3, which started from Tomopy, so they are all Tomopy algorithms, they are exclusively for parallel beam dataset, which means you cannot use it for cone beam dataset. So we have the first one, the Tomopy Nghia Vo method, and second one, Tomopy image entropy error method, which use image entropy as the error metric, and now their match routine as optimizer. And the third one is a Tomopy phase correlation in Fourier space, which find the rotation axis location by finding the offset between the first projection and the mirrored projection 180 degrees apart using the phase correlation in Fourier space. Okay, let's first try the first method. You can check it. And in the middle, we see a preview of the dataset of the projection. And on the left is a preview slice ID, which is 200 for now. So this preview slice ID, you can use it. It's going to be used during the rotation center finder for any preview reconstruction. Oh, sorry, I should have mentioned how the rotation center finder work. So when you click on Update Preview, the rotation center finder will start the calculation using the method you checked. For our case, is the Nghia Vo method. And then when it finds the rotation center offset, it's going to use that rotation offset to compute the preview for this specific slice and show that preview on the right. So here in this blank space. And we will see the method, we will see the rotation center offset defines and the preview. So if you have a specific preview that you want to absorb, you can change the slice here by switching or changing the position of this blue line, or change it directly by typing. Okay, let's still use our 200 slice. Okay, let's update preview. Those 3 Tomopy methods, they are all done on the projection domain. So typically, they should be fast. Okay, now we have our preview ready. But as you can see, it doesn't give a very good results. That's okay, because sometimes some methods, some algorithm works better, some are not. That's normal. So let's select all three algorithms, say update preview. So in this way, we would have the results from all the three different algorithms. We can compare the results from the three algorithms and pick the best one. You may need to be a little careful when you use the Tomopy phase correlation in Fourier space method. Like I mentioned before, it finds the offset between the first projection and a mirror projection 180 degrees apart. In our code, by default, we thought that your projection is over the 180 degrees, which is the case for most of the parallel beam dataset. So it's going to pick the first projection and the last projection, which is 180 degrees. But if you have a parallel beam dataset which is out of this range, for example, if you have a dataset covers from 0 to 270 degrees, it won't work. So be noticed about that. Okay, so we have our results. Preview from Tomopy here, preview from Tomopy image entropy error, and preview from Tomopy phase correlation method. They give three different results, minus 3970.75, 0, and minus 107.5 pixel. So we can see actually the third one gives a best result. Sometimes if it's too small, we have some tools for that. The third one, this one, zoom to rectangle. So when you click on it, you can press and hold. That will give you a rectangular region to zoom in. So select the smaller region here. Okay. Now that's clear. But be careful, this can be only used for the first preview. And it's going to be applied for all three views, but if you try it on the third one or the second one, it won't work. That's the only thing. Okay, also we could shift the second push button. When you click on it, you can press and hold to move the view. You can switch to the region below, switch to the region on the right. Okay, and the first one is to reset. Okay, now we have our full view. Or if still you cannot see difference from using those buttons, you can use a compare histogram. This will compare the histogram of the three previews. We can change the bin count or change it to bit log. Sometimes this histogram comparison could be informative, but I don't think so for our case. Or still, if you think it's still too small to be absorbed, you can export preview. We can export all three previews. And it's going to be published. Then you can use that you can put a ruler on the preview to see the value change. Okay, that's what we have. But in our case, it is quite obvious. We will choose the third one. So we just need to click on this radio button here. This will be selected, and you can see the selected rotation center offset on the right side will be minus 107.5. You can say OK. Now it's going to change the rotation center offset value in the geometry acquisition part. This value is now minus 107.5. Be careful, this value may not be the same as the value you had before because that dataset in the rotation center finder is in pixel, but here it's in millimeter. The reason why it's the same because we have a detector spacing of 1 in this case. If you have a different value, so this value will be a little different. But still, they are convertible. Okay. I'll just remove my 3 previews here. Okay. We can use this rotation center offset, compute preview. So that's with rotation center offset. Let's calculate another one when it is 0. 0 rotation center offset. Okay, here we can see the difference very clearly. 0 offset is kind of, we couldn't even see any feature. But with the rotation center offset, it shows a very good result. Okay, so that's 3 Tomopy algorithms. Next, I will switch my dataset to a cone-beam dataset. Okay, so this dataset is a engine part. It was shared with us by Denis Cormier from Rochester Institute of Technology. Thank you, Denis, for sharing this data with us. It has a 720 slices over 360 degrees. So it's kind of a complex dataset, not a very simple one. Okay, we can change the projection dataset and change our beam type to be cone beam. Because it's not from a specific scanner manufacturer, I will input my dataset from this preview and remove the detector offset I had before. So there are basically 2 parameters we need to determine. One is the detector offset or the rotation center offset here, and one is tilt angle. Okay, let's start find rotation center. Now there are only 2 methods available. The first one is manual range. When you click on it, you'll see 3 values here you need to change: starting offset, step, and ending offset. So these 3 values will determine a list of rotation center offset, and when you click on update preview, the manual range algorithm will do the reconstruction using those list of rotation center offset, calculate preview for each of the rotation center offset value, and show them on the right side. There is a limitation of maximum 6 previews shown on the screen, so the length of the list determined from those 3 values cannot be larger than 6. Yeah, that's why we call it manual range, because you need to select the range and choose a best one from the list you gave. And the second method is called image metric. Same thing, there is reconstruction required. According to the offset range we have, it's going to take the image metric of the reconstruction preview as a cost function, and using this cost function versus rotation offset and a optimizer, and then optimizer to find the final value, perform a optimization. So this method is an iterative method, which means it's going to take longer than the other method. Typically, how I use those 2 methods is I'm going to combine them together, because the image metric is typically to find the local minimum. When you have if you have a very big range, the local min may not be the correct rotation center offset. So what I typically do, I go to manual range, make sure I have a smaller range. for the image metric algorithm, then use that range for the image metric to find the final value. Okay, so our case, let's try -1 to 1 is too small. Let's try -20 to 20. As I mentioned, there is a limitation of maximum 6 previews. So 0.5 step size doesn't work, shows red. Let's say 10. Okay, update preview. Oh, still exists. Oh, I didn't check, sorry. So when you click on the menu range, you can select change the parameters or select whatever options you have. But to be used in the update preview options, you have to make sure that this checkbox is checked. Okay, now it should be fine. Alright, we have 5 previews from -20 with a step size of 10, -20, -10, 0, 10, and 20. Okay, so we can zoom in to see our feature. Okay, it's kind of quite obvious. For 0, 10, and 20 rotation center offset, we see a double edge. Apparently they are off. And for the dataset of -20, there is part of the shadow region in the middle, which shouldn't be there. So this is also not the best result. -10 gives the best result. So we should know that our correct value should be between -20 to 0. We can now change the ending offset to be 0. And we can use a smaller step size, 5. Let's update preview again. Right? Now they are much better. But again, -5 is not a very good result. So let's say maybe -6. And the starting offset should be something, let's say -19. Okay, and step of 3. Furthermore, we use a smaller range. Alright, we have 6 previews. Still -19, I think we can exclude that from the range. So maybe -16 for the starting. And -4, we can exclude. Even -7 is not very good. So let's say -8. Okay, we have a much smaller range. The value should be between, I think it should be between -13 to -16 because they are both very good. But for here, you can either choose to use manual range, continue using manual range algorithm to try and select. Or we can move on to image metric method using this range, -16 to -8. Let's say manual range, check manual range. Here we have 2 options of metric type, shown entropy and sharpness. Sometimes those 2 different metric would give totally different results, depending on your feature or the noise. You may need to try which one suits better for your dataset. Angular sampling factor, by default we have a 2. This is to speed up the optimization. Because it is an iterative method, we find it is very time consuming. Because we're doing the reconstruction each of the time multiple times. That's why we apply angular sampling, which means instead of 720 projections, we use only 1 out of 2 projections, so 360 projections. It's going to make it faster. And here we see a curve window. This has nothing to do with optimization, but just for you to choose the appropriate range for the optimization. For example, before we have minimum of 16 and 8, we know the correct value is definitely within that range, sorry, minus 8 here. So we can plot a metric cost function curve versus the rotation center offset. So it's going to select 10 points from minus 16 to minus 8 and compute the preview, calculate the shown entropy metric, and plot the curve. So we can compute curve. Let's try that. It's not necessary for the optimization process to do this curve plot, but just for you to have a better idea and avoid finding a wrong value in another local minimum. Okay, so apparently we see a minimum at some point around minus 14. That should be our rotation center offset. So instead of using this minus 16 to minus 8, we can furthermore make our range smaller by moving this yellow line. Minus 14, we can go here. Minus 14, you can see when I move the position, the minimum offset over here changing. And this one could be minus 20, something around here. And for the optimization parameters, we have starting offset range from minimum to maximum. So for each of the optimization, it's going to pick a random number within this range as a starting point, and the optimizer will run the optimization with this precision, by default 0.1, and get the final value. Also, we have a number of optimizations here. By default, it's 2. You can change it to be 3 or 4 or 4 or 5. Why we have this number of optimization is we found this method sometimes is very easy for this algorithm to find a wrong value, because there might be some local minimum, and if you have a specific starting points, it doesn't, right? It's gonna be tracked in that local minimum, so it couldn't find the correct result. So we have multiple optimizations, because for each of the times the starting point is random. So in this way, at the end, we compare the results from different optimizations, find the one gives the best result, choose that one. So that in a great degree, we avoid a local minimum, make sure we have the correct value. Okay, now we have our parameters, minimum, maximum, number of optimization, and precision. We can start update preview. This may take a little longer. Okay, 33% finished. This means one of the optimizations has been done. Great, we have our result. Keeps the selected rotation center offset is minus 13.901. We see a very good result. We can click export preview. We have this preview of image metric minus 13.90. Select rotation center offset and OK. When I click OK, this value will change the value of the detector offset on X. Again, because they have different unit. The one in the rotation center finder is in pixels, but here we have in millimeter, and also the other one is the rotation center offset of the object, and this one is a detector offset. So you have to multiply by -1 to convert it to the other one. That's why they're different. Okay, let's compare. We have our preview. Let's compare. Check this one. Oh, sorry, I saw a beam hardening correction was checked over there. I'll just uncheck it. To be fair, let's recalculate the previews. Okay, compute preview. This is for the image metric. And let's calculate one with 0 offset. No calibration. Okay, we see a great improvement over here. I just showed 5 different algorithms for the rotation finder, but if you remember at the beginning we mentioned we have actually 6. The last one is actually hidden in the tilt angle finder. Sorry for that. I know that is not a very good design, but that is what we have at the beginning. So this will be changed in our next release. We will put that algorithm under the menu of rotation center finder as well. But for this version, it's going to be together. So in the tilt angle finder, we have a method of sum of projection. This method, it uses the symmetrical characteristic of the sum of the projections. Calculate the sum of projections for all the projections over 0 to 360 degrees. If it is a perfect geometry, there's no offset. It should be symmetrical along the central axis. But actually, because we have both the tilt and also the detector shift, this may not be the case. So we'll use that to have a cost function and to do the optimization using that cost function. So this method could be used to find either tilt angle or rotation center offset, or both at the same time. Okay, we had a very similar design here. For tilt angle, we have a minimum tilt angle, maximum tilt angle, and optimization. Same thing for the rotation center offset. And below, we have a curve plot region. Again, this is not necessary for the optimization, but it's going to help you to take a look at the curve and make your decision. For example, if you want to plot the curve for the cost function versus the tilt angle, you can choose the X label to be tilt angle. Rotation center offset, let's say just make it 0. Number of points, how many points, data points you want, by default is 5. If we click refresh curve, it's gonna calculate the cost function between -3 to 3 with 5 different data points. Okay, here we see a local minimum between 0 to 1, close, should be something like 0.2 or something like that. That's gonna help you again to use a smaller range. Because we know it's something between 0 to 1, we can change this to be -1. And this way the optimization will be faster. But anyway, because this method is only done for the projection domain, so there's no reconstruction involved, itself is already very fast. Okay, we can check the fine rotation center offset. So this is a little small. We uncheck this one to have this value shown. Mean rotation center offset, because we have tried, we know it should be something between -16 to -8. Let's change this to be -20. Okay, and check both the tilt angle finder and the rotation center offset. Maximum iteration number. Because when you check both tilt angle and rotation center offset, how it works is it's going to have an initial tilt angle and the initial rotation center offset. First, run the tilt angle finder with the initial rotation center offset, have a tilt angle value, and then use that tilt angle value to replace the initial tilt angle, and use that tilt angle to find rotation center offset. So that's we call it one iteration. And we have a maximum iteration number of 10 to limit the number of iterations. And this apply interpolation is used to check if you want to apply linear interpolation between two pixels or not. Because how it works is it has a sample projection, and it's gonna, for example, if you want to do a rotation center offset, it's gonna shift the image to a certain offset and compare the original sample projection image and the one after shift by comparing the value for each of the pixels. But if you have some small value, for example 0.1 pixels, you may not have the values at the exact same place. Then you can choose I want to do a linear interpolation to compare the values. Let's apply interpolation push button here. Okay, now I think we have all the values set. We can say compute. Optimization succeed. Okay, we have the optimal tilt angle is 0.581 and the optimal rotation center is -14.386. You would find that this value rotation center offset is a little different with the one we had from the image metric, which is -13.7 or something. This is normal because we have changed our tilt angle, so the rotation center offset will be changed as well. Okay, we can see apply. Now we have our detector angle, in-plane angle 0.581, and our detect offset as 1.439. Okay, we can close. Let's try compute a preview using this algorithm. I would change the title of it as sum of projection. Okay. Let's compare the two previews. From the image metric. Okay, this is the one from image metric, and on the right we put that of the sample projection. Okay, we can see they're both very good, but here with the sample projection, with the tilt angle corrected, we have a clearly boundary over here than a blurry region in the corner here. So we have seen a great improve. That's basically all I want to show for the geometry calibration part. Thanks for watching my video again. See you in our next video. Bye bye.